So here I'm going to let you know the answer to the last question. Work isn't a property. I think you probably should know that. Work is not a property. It is path dependent, is direction sensitive. Okay? We cannot write delta work. Okay? If you write delta, it just means you don't need to know state 1 or state 2. This is not a thing. Okay? We are going to always have to integrate it and know exactly what path we're following. Okay? We're going to have to worry about dW. It's path dependent, direction sensitive. It's direction sensitive. Okay. Now, I want to talk to you how we're going to be dealing with work in this class. Okay, so let's write this out here. Work is equal to F times X. All right, so let's write this in differential form. dW is equal to F dx. So it's an inexact differential and a normal differential here. Okay, what is force? Well, in this class, we're going to be dealing with pressures times areas to give us the force. So I'm going to write this as pressure times area times dx. So this is what this is. Force is written as pressure times area. Okay, now look at this. What is area times dx? If I take an area and I move it through a distance x, what do I sweep out? I sweep out a volume. So this is going to be dW is equal to P times dV. So most of the time in our class, because we're dealing with pressures, work is going to be the integral from 1 to 2 of P dV. Okay. Now this type of work has a special name. When you're looking at pressure as it changes here, let's look at this. Here's my piston cylinder. I have volume 1. I have volume 2. Volume 1, volume 2. If the pressure is helping us here, this is called boundary work. There are many types of work that you can be dealing with. But this is the first time we'll talk about is boundary work, when the boundary is changing. Now notice here in this piston cylinder, this closed system, the boundary is changing. Let's pretend like we have air in there. This is a cross section. Notice that the mass of the air, we're not having any place for the mass of the air to leave. We're not crossing, we're not having, it's still a closed system. Still a closed system. But the boundary is changing. The mass is either being compressed or expanded. Okay, boundary work. Okay, now the thing you need to know about this equation here, this pops out the thermodynamic sign convention. I'm writing too fast. My writing is not very good. Let's look at that. What is it going to show us? Well, work. Let's consider constant pressure work. Okay, constant pressure work. Pressure is going to come out of here. We're going to have V2 minus V1. V2 minus V1. Okay. Let's say that our volume 1 is here. Volume 2 is here. Okay. V2 is greater than V1. So we're going to be going from here all the way up to here. There's expansions happening. What's happening? That piston is moving up. It's pushing stuff out. It is working on the surroundings. That's positive. Exactly what our equation shows. Now let's have a situation where V2 is less than V1. Here's V1. Here's V2. What has happened? Compression has happened. V2 is less than V1. We are going to have a negative sign in our equation, and you will see that the surroundings are pushing on that system, causing it to be compression. So this pops out the thermodynamic sign convention, exactly what we want it to happen. Another way we can write this, instead of writing it with volume, we can write it with specific volume here. So we could write work is equal to pressure times mass 2 times specific volume 2 minus mass 1 times specific volume 1. But since we're dealing with closed systems and mass 2 is equal to mass 1, we could write this as work is equal to pressure times mass times V2 minus V1. So that's another way to look at this. Or work is equal to mass times the integral from 1 to 2 of P d little v, the specific volume. That's another way to write about it. All right. Last thing I'm going to do here. Remember, we can draw ourselves a pressure, specific volume, or specific pressure volume diagram to look at how visualize work. Okay, so here we're going to go from point 1 to point 2. Okay, let's just see that our path, maybe this is our path. Work is the integral of P dV. How do we visualize that? The integral, what is an integral? An integral is the area under a curve, right? So the area under this curve, this is equal to the work 1 to 2. Is it positive? Okay, we're expanding, it should be positive. Now work 1, 2, that's going to be greater than 0. Now let's say we're going to go back from 2 to 1. We're not going to go the same path, we're going to go back this direction. Work is the area under the curve. This work 2 to 1, we're compressing it. It's going to be less than 0. Okay. Direction sensitive, that tells you about the sign. Path dependent, tells you about the magnitude. What we're going to have inside of here is going to be our network. Oh, that's going to be all confusing as all heck to look at. This is going to be our network if we were to say what we have, and we'll talk about that more. Work net is going to be equal to work 1, 2 minus work 2, 1, and we'll put magnitudes on that. We'll get to that more often, but understand this. If you can look at work and understand it by talking about integrals, if you can look at it talking about the pictures, if you can draw a diagram for it, it's going to help you out a lot. Understanding the signs, understanding the thermodynamic philosophy is going to really help you here. We are going to continue talking about work in our next lecture, where we're going to talk about methods of work that we can do some of work in this mode that we'll be discussing, integral of PdV, the boundary work. Okay, but until then, I hope you have a good rest of your day, and we'll see you in class when you get a chance.